Assalamualaikum and hello everyone. Today, my group consisting of me, Puteri AREENA SOPHIA, SITI Ellyana and NURUL NAJIHAH will be presenting our laboratory video for experiment T4 heat pump conducted under the guidance of Dr. Muhammad ARIF bin JALIL. First and foremost, we have four main objectives for the experiment: to demonstrate the principle of heat transfer, to study the refrigeration and heat pump cycles, and to learn how to use a refrigerant data sheet and pH charge. Apparatus used to carry out these experiments including a water-to-water heat pump unit, a stopwatch, and a measuring cylinder to calculate our flow rates. A heat pump is a refrigeration machine that uses electrical energy to transfer heat from a lower temperature area cold source to a higher temperature area heat sink. The reversal concept, while a refrigerator is focused on the cooling effect QL, a heat pump operates on the same vapor compression cycles but focused on utilizing the heating effect QH rejected to the warmer space. Refrigerants, the system uses R134A as the working fluid or heat carrier, which changes phases to absorb and reject heat. This schematic diagram shows the layout of our system, showing bucket A as the evaporator, bucket B as the condenser, the temperature and pressure sensors, and the viewing glass used to observe phases changes. Compressor, draw in low pressure vapor and compress it to high pressure and temperature. Condenser, which is bucket B, high pressure vapor reject heat to the surrounding water, condensing into a liquid. Expansion valve, throttles at the highest pressure liquid, dropping its pressure and temperature, while bucket A is evaporator, low pressure liquid absorbs heat from the water, evaporating back into a vapor. To evaluate thermal performance, we calculated the heat loss in evaporator using QL equals to MC delta T and heat gain in condenser QH equal to MC delta T, which delta T is equal to T out minus T in, and M is the water mass flow rate. The pressure enthalpy diagram of pH charge. It visually maps out the cycles against the refrigeration saturation zones, plotting pressure vertically and enthalpy horizontally. The cycle consists of four processes. 1 to 2 is isentropic compressions, 2 to 3 is constant pressure heat rejections, 3 to 4 is a constant enthalpy expansions, and 4 to 1 is a constant pressure heat additions. Coefficients of performance. Unlike efficiency, which cannot exceed 100%, a heat pump performance is measured by COP, which is usually greater than 1 because it moves existing heat rather than creating it. This is the equation, which is heating effect divided by power consumed, where W in is the electrical power consumed by the compressor, 135 watt according to data sheet.
Procedure for part A. Number 1, the main water supply was turned on and the evaporator and condenser water flow rates were set by a process of trial and error. The coils in both bucket A and B were made sure to be fully immersed underwater at all times. The condenser flow rate was made sure to be as low as possible. Number 2, all the thermometers were placed in the proper points as in the schematic diagram shown in figure 8.1. Number 3, the condenser and evaporator inlet temperature TC in and TE in were measured. Number 4, the measuring cylinder and stopwatch were used to measure the condenser and evaporator water mass flow rates ME and MC for 1 minute. Number 5, the condenser and evaporator outlet temperature TC out and TE out and the initial readings at T equal to 0 second of all the other thermometer T1, T2, T3 and T4 and pressure gauge P1 and P2 were measured. All the readings were recorded in table 1. Number 6, compressor was switched on and step 4 was repeated every 5 minutes until pressure P2 was about 10 bars gauge and all the data was recorded in table 1. This is data for part A. Since part A, number 1, calculate the average heat transfer in the evaporator. Heat lost by water in evaporator for bucket A, we use QL equal to water mass flow rate in bucket A times with specific heat capacity and times with delta TE, where delta TE equals to TE out minus TE in. Analysis part A. Number 1, calculate the average heat transfer in the evaporator. When T equal to 0 minute, we use QL equal to ME times with specific heat C times with delta TE. Then we get QL equal to 0 joule per second. When T equal to 5 minutes, we use the same equation and we get negative 2,1992.08 joule per second. When T equal to 10 minutes, we get QL equal to negative 5,1984.16 joule per second. When T equal to 15 minutes, we get negative 6,000 and 732.18 joule per second. When t equal to 20 minutes, we get negative 6,732.18 joule per second. And then we calculate the average of QL, we get negative 4,488.12 joule per second. Number 2, we calculate the average heat transfer in the condenser. Heat gained by water in condenser for bucket B, QH equal to water mass flow rate times with specific heat capacity times with delta TC. Delta TC is equal to TC out minus TC in. Number 2, we calculate the average heat transfer in the condenser. When t equal to 0 minutes, we get QH equal to 0 joule per second. When t equal to 5 minutes, we get QH equal to 15,804.6 joule per second. When t equal to 10 minutes, we get QH equal to 22,126.44 joule per second. And when t equal to 15 minutes, we get QH equal to 28,448.28 joule per second. When t equal to 20 minutes, we get QH equal to 31,609.2 joule per second. Then we calculate the average of QH. We get QH equal to 19,597.7 joule per second.
Analysis Part A, determine the average COP of the heat pump. We use the formula QH dot over W in dot, where W is the electrical power consumed by the compressor, which is 125 watt according to the data sheet. So when T is equal to 0, COP is 0. When T is equal to 5 minutes, COP is 126.44. When t is equal to 10 minutes, COP is 177.01. When t is equal to 15 minutes, COP is 227.59. And when t is equal to 20 minutes, COP is 252.87. In order to find the average COP of the heat pump, we will have to add 5 COP and then divide by 5. And the average COP will be 156.78. Now, let's proceed to the procedures for Part B. First, when the pressure P2 was about 10 bars gauge, the condenser and evaporator water flow rate in were increased and the water outlet in both condenser and evaporator valve were modified to maintain steady flow rate. Second, measurement as in steps 3, 60 seconds of water collection, and steps 4 in Part A were repeated for every 5 minutes. Third, step 1 was repeated once or twice or until the condenser water flow rate was too high, about to overflow the bucket. Fourth, snapshot was taken. The observation of the refrigerant inside the viewing glass A and B was observed and recorded. This is the data recorded for Part B. The first analysis for Part B, we need to plot the pump cycle on the pressure enthalpy pH diagram of the R134A refrigerant. So we first need to find the absolute pressure, which is P gauge plus atmospheric pressure. For MC1, P1 is equal to 0.4513 megapascal, P2 is 1.2013 megapascal, and for MC2, P1 is equal to 0.4513 megapascal, and P2 is 1.1013 megapascal. Next, for MC3, P1 is equal to 0.4513 megapascal and P2 is equal to 1.0513 megapascal. For MC4, P1 is equal to 0.4513 megapascal and P2 is equal to 1.0513 megapascal. Lastly, for MC5, P1 is equal to 0.4513 megapascal and P2 is equal to 1.0513 megapascal. To plot the pump cycle, we use the value below for each state and repeat the same things with t equal to 10, 15, 20, and 25 minutes. So for state 1, we use the value of P1 T1, state 2 we use the value of P2 T2, state 3 we use the value of P2 T3, and also state 4 we use the value of P1 T4. This is the pump cycle for MC1, which is t is equal to 5 minutes. This is the pump cycle for MC2, where t is equal to 10 minutes. This is the pump cycle for MC3, where t is equal to 15 minutes. Next, this is the pump cycle for MC4, where t is equal to 20 minutes. And the last one, this is the pump cycle for MC5, where t is equal to 25 minutes. So, after plotting the pump cycle, the summarized value for H1, H2, H3, and H4 in the t is equal to 5, 10, 15, 20, and 25 minutes are as below. For the second and third analysis for Part B, we need to determine the W in, QH, QL, and COP from the pH diagram using the equation 8.3, 8.4, 8.6, and also 8.7. And for the third analysis, we need to repeat the step 1 and step 2 for different MC and ME. So, as shown in the picture in this slide, so these are the equations that we are going to use, which is 8.3, 8.4, 8.6, and also 8.7. For MC1, the WIN dot value is equal to 13.41 kilowatt, QH dot is equal to 73.38 kilowatt, QL dot is equal to 38.59 kilowatt, while the COP is 5.47. For MC2, the value of WIN dot is equal to 35.45 kilowatt, QH dot is equal to 224.50 kilowatt, QL dot is equal to 148.88 kilowatt, and the COP is equal to 6.33. For MC3, the WIN dot is equal to 38.09 kilowatt, QH dot is equal to 262.58 kilowatt, QL dot is equal to 183.13 kilowatt, and COP is equal to 6.89. For MC4, the WIN dot is equal to 70.35 kilowatt, QH dot is equal to 497.48 kilowatt, QL dot is equal to 248.76 kilowatt, and the COP is 7.07. For MC5, WIN dot is equal to 55.97 kilowatt, QH dot is equal to 395.80 kilowatt, QL dot is equal to 293 kilowatt, and COP is equal to 7.07.
As for our discussions, a heat pump operates using the vapor compression's refrigerant cycle, in which the refrigerant absorbs heat from a low temperature region to a higher temperature region. In this experiment, R134 refrigerant was used as the working fluid. The evaporator absorbs heat from the surroundings, while the condenser releases heat to the surroundings. The average heat transfer in the evaporator was calculated as QL equals to negative 4,488.12 joules. The negative sign indicates that the heat was absorbed by the refrigerant during the evaporation process. Meanwhile, the average heat transfer in the condenser was obtained as QH equals to 19,597.70 joules. This positive value shows that the heat was rejected by the refrigerants to the surroundings in the condenser. The coefficient of performance of the heat pump is given by QH divided by WIN. The average COP obtained in this experiment was 156.78. This value is much higher than the normal range for practical heat pump systems.
Discussion for Part B. In Part B, the heat pump cycle was plotted on the pressure enthalpy pH diagram of the R134A refrigerant for 5 different operating times, namely as 5, 10, 15, 20, and 25 minutes. The pH diagram is an important thermodynamic tool because it illustrates the change in pressure and enthalpy experienced by the refrigerant throughout the cycle. By using the measured pressure and temperature at each stage point, the corresponding enthalpy value H1, H2, and H3, and also H4 were determined from the R134A refrigerant chart. State 1 represents the refrigerant entering the compressor as a low pressure vapor. State 2 corresponds to the high pressure and high temperature vapor leaving the compressor. State 3 represents the liquid refrigerant leaving the condenser after heat rejection, while State 4 represents the low pressure and liquid vapor mixture after passing through the expansion valve. Since the throttling process in the expansion valve is an isentropic process, the enthalpy remains the constant during the expansion, so H3 equal to H4. From the obtained enthalpy values, the compressor work input, condenser heat transfer, evaporator heat transfer, and coefficient of performance were determined for each operating time using the thermodynamic relation. As the operating time increased from 5 to 25 minutes, the thermodynamic state point shifted slightly off the pH diagram. This occurred because the temperature and pressure of the refrigerant gradually changed as the system approached a steady state operation. The compressor continuously increased the pressure and enthalpy of the refrigerant, while the condenser rejected heat and reduced the refrigerant enthalpy. The expansion valve then caused a sudden pressure drop without changing the enthalpy, and finally the evaporator absorbed heat to increase the refrigerant enthalpy again. The plotted cycle therefore clearly demonstrates the complete vapor compression heat pump cycle of the R134 refrigerant.
Discussion Part C. During the experiment, the refrigerant observed in viewing glass A appeared to be much less compared to viewing glass B, while viewing glass B appeared almost completely filled with refrigerant. In addition, bubbles were observed in both viewing glasses. These observations can be explained by considering the thermodynamic state and phase of the refrigerant at different sections of the heat pump system. Viewing glass A was likely located in the low pressure region of the system, near the evaporator or after the expansion valve. In this region, the refrigerant exists mainly as a low pressure liquid vapor mixture. After passing through the expansion valve, the refrigerant experiences a sudden pressure drop, causing part of the liquid refrigerant to evaporate instantly in a process known as flash evaporation. As a result, the refrigerant occupies a larger volume and appears less dense inside the viewing glass. This explains why the amount of visible refrigerant in viewing glass A was relatively low. The bubbles observed observed in viewing glass A were caused by the presence of vapor bubbles within the liquid-vapor mixture due to evaporation under low-pressure conditions. On the other hand, viewing glass B was likely located near the condenser outlet where the refrigerant existed mainly as high-pressure liquid refrigerant. In this region, most of the refrigerant had already condensed into liquid form after rejecting heat in the condenser. Liquid refrigerant has a much higher density than vapor refrigerant, therefore the viewing glass appeared almost completely full. However, bubbles were still observed because complete condensation may not have occurred at every moment during operation. Small vapor bubbles may remain due to slight pressure fluctuations, incomplete condensation, or the presence of entrant gas within the refrigerant flow. In addition, during transient operation before reaching steady state, the refrigerant flow rate and temperature continuously change, contributing to bubble formation in both viewing glasses. Overall, the observation of viewing glass A and B clearly demonstrated the phase changes of the refrigerant throughout the heat pump cycle. The presence of both liquid and vapor phases confirmed that the refrigerant underwent evaporation and condensation processes continuously within the system.
In conclusion, this experiment successfully demonstrated the principle of heat transfer, heat exchanger operations, refrigeration cycles, and heat pump cycle using R134A refrigerant as the working fluid. The processes of compressions, condensations, expansions, and evaporations were clearly observed through the measured temperatures and pressure of the systems. The heat transfer rate in the evaporator and condenser, as well as the coefficients of performance of the heat pump, were successfully determined. In addition, the refrigerant data sheets and pressure enthalpy chart were used to obtain the enthalpy values and plot the heat pump cycle for different operating times. The observations from the viewing class are also confirmed the phase changes of the refrigerant throughout the cycles. Overall, the experiments provided a better understanding of the operations and thermodynamic performance of refrigeration and heat pump systems. To wrap things up, this is our key idea from our behind presentations, while this is the references that we use to get the more information about the heat pumps. So let me conclude these presentations. Thank you for listening.